In this video, we're going to start a new chapter. We're going to start learning about what are called exponential functions. And to begin with, we're going to work in material that's covered by 6.1 and 6.2 of the textbook. This video is just an introduction to the idea of exponential functions. We'll work on more specific problems in the later videos. So what I'd like to do here is consider two functions, g of x and f of x, with the given tables of values, 0, 5, 1, 8, 2, 11, 3, 14, 4, 17, 5, 20 for g, and 0, 5, 1, 15, 2, 45, 3, 135, 4, 4055, 5, 12, 15 for f. And in order to try to figure out what's going on with these functions, let's plot the points for both and see what we can find out here. So I had some graph paper here that I prepared ahead of time. And for g, let's see, we have 0, 5. And 1, 8, 2, 11, right there, 3, 14, and 4, 17, and 5, 20. And I think you can see that these points line up along a perfectly straight line. Again, this is the graph of the function g in our example. Well, that's a linear function, right? We can see from the graph that those points line up exactly. And so g is linear. What about f? So let's plot some points for f here. Now, in order to fit some of these y values on for f, I changed my scale on the vertical axis. So while my horizontal axis is still just 1, 2, 3, 4, so on and so forth, on my vertical, I'm squeezing things together a little bit so I can fit some of these larger values. Also, I guess I did spread out my horizontal axis values a bit, but as long as I'm consistent, that's just fine. Using 2 squares for each unit going across the horizontal. So let's go ahead and plot. Now, 0, 5, I can barely fit that point on here, right? Because my first tick mark is at 25, so 0, 5 is going to be very close to the horizontal axis, x-axis here. 115 is just going to be a little bit larger through that square. 245, okay, now I'm almost up to the line at 50. 3, 135, this is 150, 125, so 3, 135, there on this scale. 4, 405, so I got to go all the way up to, here's 400, so 4, 405 is just going to be slightly above 400 there. The point at 5, I can't even fit on here, right? It's way up there. And so what I see is, if I imagine connecting these points up with a curve, this is definitely not linear. My guess would be a graph something like so that keeps going up and up and up. So the function f has this kind of shape, and that's what we're going to start looking at more closely. But before we start talking more about graphs, I want to say some more about these tables of values. So we have already seen that g is a linear function, and in fact, we can see that going from one point to the next, we can go up 3 over 1, up 3 over 1. That's like rise over run, which is 3 over 1, which is the slope of that line. So g is a linear function with slope 3, and we plotted the y-intercept at 5. So m is 3, b is 5. We can write a formula for g of x, 3x plus 5, a linear function that we're very, very familiar with. And we observe that f is not a linear function. For a linear function, for the linear function g, the function values, the y values of the function, always increase by 3, the slope, as we increase the inputs, or the x values, by 1. So what I'm saying is, here's the table of values for g again. As we increase the x's by 1 each time, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, the corresponding y values always increase by 3. 5 plus 3 is 8, 8 plus 3 is 11, plus 3 is 14, plus 3 is 17, plus 3 is 20. In fact, that's sort of a numerical way of thinking of what the meaning of the slope is for that line. Now let's take a look at the table of values for f. And what I want to observe first of all is we do not have a similar pattern for the values of f. If we increase x by 1, as we work our way through the table, the corresponding increases in f change. From 5 to 15, we're adding on 10, right? 5 plus 10 is 15. 15 plus 30 is 45. 45 plus, it's actually plus 90, will be 135. 135 plus, let's see, 405 minus 135 is going to be 270. And when we increase from 405 to 1215, I think that's actually 1215 minus 405 is 810. So these changes in the y values are getting larger and larger, even though x is just increasing by 1. And we can think of that as being reflected by this graph kind of turning the corner and shooting up in a very steep way. But now it turns out we can find a pattern to how the function values of f are changing. For f, the function values, or the y values, get multiplied by 3 as we increase the inputs, or the x values, by 1. So let's take a look at what that means on the table again. I just want to remind us that we just kept looking at increases of 1 in the x values. And the pattern here on the right, or one way to think of this pattern, is it's like we're multiplying by 3 times 3. 5 times 3 is 15. 15 times 3 is 45. 45 times 3 is 135. 135 times 3 is 405. And if we multiply by 3 again, we get that 1215. So instead of adding the same amount to the y values, which is the pattern we saw for a linear function, for this kind of function, we multiply the y values by the same amount as we work our way through the table. And this multiplication property is particular to a new kind of function, and we call these new functions exponential functions. So we're going to start studying exponential functions here that will have graphs very similar to this picture we saw from our table, a graph we got for the function f. Now, I'm actually going to show you a formula for f. I had a formula when I set that problem up, and it looks something like this. F of x equals 5 times 3 to the x power. Notice that the input variable x is an exponent here. Exponential functions are functions that have an input in the exponent, in the power, right? And I just want to go back to our thinking about our table again one more time and just convince you that this formula gives us the f function values that we saw earlier. So let's take these x values. I'm going to plug them into my formula for f. F of 0 would be 5 times 3 to the 0, which is 5 times 1, or 5. F of 1, if I use this formula, is 5 times 3 to the 1, which is 5 times 3, or 15. F of 2 is 5 times 3 to the second power. It's actually 5 times 9, and 5 times 9 is 45. F of 3 would be 5 times 3 to the third. That's 5 times, now 3 to the third is 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. So that's 5 times 27. 5 times 27 is going to be exactly 135. F of 4 is 5 times 3 to the fourth. That's 5 times 3 times 3 times 3 times 3. That's actually going to be 27 times 3. 27 times 3 is 81. 5 times 81 is 405. And finally, for here, this table value, we have 5 times 3 to the fifth power is 5 times, that's 3 multiplied by itself. 5 times 3 times 3 times 3 times 3 times 3 is going to be 243. I think it's the same thing as 3 times 81. 5 times 243 is 1215. So I see that the y values I got here are the same as the f of x values, the y values I gave you right at the beginning of this video, and that we graphed for the function f. So this definitely is a formula for that function. So that's the end of our introduction. We're going to look a little deeper into exponential functions in the next video.